Hello. Are you guys feeling better for the midterm coming up tomorrow now? Since yesterday, last night? Wait, what did you guys do today during lecture? Was it a review session for the midterm? Or did she move on? Well, I think no, I don't think she has time for that. Yeah, I think she started final material. Yeah. Pure cyclic reactions like the ring opening, ring closing, thumb rule, conrelatory, disrelatory. I see. So these are the topics that people ask me to do in um, this office hours. So I'll go over these first, and then we could go over the electrocyclic ring opening, ring closing at time if we have time, right? So let's go over the chapter 14 reactions worksheet, C, D, and U. So what reaction do you guys think this is going to be when you have these reactants reacting with heat? What is the reaction name? Right. Diels order, right? Because our diene backbone here is going to be that. Our dienophile backbone is going to be this. So once we have located our diene and a dienophile backbones in the Diels order reaction, we're going to draw the pocket between them like that, right? Where I'm going to number these atoms 1, 2, 3, 4, 5, 6 for the Diels order reaction. Okay, so now, yeah, right. We are going to now look at the charges of this dienophile and diene, right? So we know that these R groups here are EDGs, putting negative charges on atoms 4 and 1, right? Because if we imagine them to have negative charges, like lone pairs of electrons, if this were to donate electrons into the system like this, there's going to be a negative charge here. If we donate electrons into here, there's going to be a negative charge there. So there's negative charges on both carbons here, right? There's also going to be partial positive charges on both carbons on a dienophile because these are two EWGs right here, right? But this one is going to be a stronger EWG because it's actually withdrawing electrons by resonance. But this one here is withdrawing electrons by induction, right? So we're going to get two sets of enantiomers here. Would these ethyl groups here be considered out groups or in groups for the Diels-Alder reaction? Out groups, right? Because they're going outside of the pocket. So would that make them cis or trans to the EWGs, where these are the EWGs here? Would they be cis or trans to the EWG according to the endo rule? Cis, right? So now, yep, it's correct, cis. If I draw out the product like this, where this is going to be 1, 2, 3, 4, 5, 6, the phenyl group at carbon 2 is going to stay flat and planar because it stays on an sp2 atom, right? Where if I make my ethyl groups dashes, the alkyl groups dashes, that would also make the EWGs here dashes because we said that they're going to be cis to each other, right? And in this case right here, since we see that these EWGs are also cis to each other in relation to the dienophile, like they're on the same side, then we maintain that cis configuration right there, right? So both EWGs would work here, right? If they were to be trans like that, then we're actually gonna get like uh 1, 2, 4 sets of enantiomers, so 8 products. But in this case, since they're cis, we're only gonna get 2 sets of enantiomers, so 4 products, right? Where this is one of the products and the enantiomer of it, so this is gonna be racemic. The other product is gonna be if we flip the dienophile upside down. And if we flip the dienophile upside down, this is what we get, right? Everything stays the same on the diene side, but in the dienophile, those two groups change like that, right? Does that make sense for everyone? Why this is going to be the other product? Wait, let me just make sure just in case. Yeah, both would be racemic. Does this make sense on like why I got this product, like the flipped dienophile? It's because the charges here are going to be still aligned when I flip them. Right, when I went over this Diels order concept last night on the review session. Oh yeah, it's frozen. Oh my gosh. Let me see. Uh, yeah, screen is frozen. Let me see. Okay. Okay. Share screen again. Okay. So what I got here was where I flipped the Diana file upside down, where the fluorine is now going to be at the top side and the carbonyl is going to be at the bottom side in relation to the phenyl group. The reason why I was able to do that is because when I flip the Diana file upside down, the charges here are still aligned. So we could still go through with the reaction, right? Does that make sense for everyone for this problem here? Or does anyone have any questions on this problem? Right. And this is racemic because instead of all wedges, these could have been all, I mean, instead of all dashes, this could have been all wedges. Right. So they're cis because the out group is going to be cis to the EWG according to the endo rule. And these two EWGs here, the fluorine and the carbonyl, are going to be cis to each other because we see that they are cis to each other in the dienophile, right? If we make that line through that double bond right there, we see that the carbonyl and halogen are cis to each other, which is why we maintain that cis configuration for the dienophile portion here of the product, right? But the reason why this ethyl is cis to the EWG is because of the endo rule, right? So the EWGs are cis because they started cis to each other. The out group is cis to the EWG because of the endo rule. And if these are the endo products, would this be the kinetic product or the exo product? Right? Like, yeah, kinetic product. So endo product is the kinetic product. Yeah. So I'll explain why there's partial negative charge on carbon 1 and carbon 4 again. It's because if we have a diene with an EDG on it, like let's say alcohol, this EDG can donate electrons into the diene like this, giving a negative charge on the other end, right? So if you see an EDG on the diene like that, it's gonna supply a negative charge on the other end of the diene like that, right? This R group right here, the ethyl group, is an EDG supplying this negative charge on the other end of it, right? So this negative charge right here at carbon 4 is coming from the EDG on carbon 1. Whereas the negative charge on carbon 1 is coming from the EDG from carbon 4, right? So that's where we get the negative charges from, right? Okay, let's move on to any more questions on this problem before we move on to the next problem? Yep, no problem. Okay, let's move on to the next one. So for D right here, we're reacting a conjugated diene with excess HBr in cold conditions. So are we going to look for the thermodynamic product or the kinetic product here if we are in cold conditions? Kinetic product, right? Which means that we're going to look for the more stable intermediate or the more stable alkene product. More stable intermediate, that's right. And because this conjugated diene here is asymmetric, we're going to have to react with both alkenes with HBr to get two different resonance sets. And then from those two resonance sets, you choose the best one. You only look at one resonance set, and then from there, you look at the kinetic product, which intermediate is going to be the most stable to get your kinetic product, right? So I'm going to react the left alkene in purple. Oh, wait, green. HBr. Let's say this is A, this is B. where do you want your carbocation to be? Like, what's going to be your most stable carbocation, A or B? Right, so if there's a carbocation at A right here, this carbocation right here cannot do resonance, right? Because this is an sp3 atom and this is an sp3 atom. Whereas if we put a carbocation at B, this carbocation here is at the allylic position. That's the most important thing here about this mechanism. This allylic position here allows this carbocation to become more stable because it could do resonance like that. So the carbocation at this carbon here is actually going to be more stable than the carbocation here, right? Which means that this carbon at the left is going to get protonated by the HBr to give us this carbocation intermediate here, right? We want this carbocation at the right side because it is allylic. It could do resonance with the double bond like that. So if I draw that out, we're going to get this resonance structure here, right? Okay, so now let's react HBr with the other alkene in pink. Which carbocation, A or B, would be more stable? What position, A or B, do you want the carbocation to be at? This one is a bit more clear because the substitution and allylic position are going to be the same. Yeah, A. Right, so if we want A to have the carbocation, we're going to protonate the other carbon to give us this structure here. Right, and we could do resonance to get us this carbocation here. Right, now let's analyze the carbocations. This is a secondary allylic carbocation. This is a primary allylic carbocation. This is a secondary allylic carbocation. This is a secondary allylic carbocation. What resonance structure do you want to keep? The green one or the pink one? Pink one, right? Because they have more stable intermediates. So we're just gonna ignore the green one entirely, right? And from the pink resonance set, which one is gonna give you the kinetic products? A, B, or is it both? Are they both equally substituted, equally stable, the intermediate? Yeah, it's gonna be both. They're both equally stable. They're both secondary allylic, so they're both gonna give the kinetic product. The kinetic product is gonna come from both intermediates here, right? So when, what was it? Yeah, Br, bromine minus, comes in to attack the carbocation, we're gonna get these kinetic products here. One is gonna be that, the other one is gonna be this right here, right? Now, this is gonna be the answer if you have one equivalent of HBr, right? But we don't have one equivalent of HBr. We have excess amount. So now we're gonna react the alkene, each alkene here with HBr, right? So notice how both carbons here will give you the equal carbocation. Let's say that I draw in the carbocation for each carbon of the alkene like this. Right, that's one of it. This is gonna be the other one right here, right? And from this one, we're gonna get this carbocation and this carbocation here. Do these four carbocation intermediates make sense so far? I'm just basically putting a carbocation on all of the sp2 carbons here, right? So that one makes that, this one makes this one makes that, and this one makes that. So I'm just putting a carbocation on all of those sp2 carbons. Right. Okay. So now once we have the carbocation intermediates there, I'm just gonna put a bromine on each carbocation, right? So bromine here, because that's where the bromine minus is gonna attack. Bromine here, and a bromine here, and the bromine here. So those are all the products that we're gonna get, right? But there's 3 unique ones, and I'm gonna highlight the unique ones in yellow, right? This is a unique product that we'll get. This is another unique product that we'll get. And this is another unique product that we get, right? This one here is not unique because this one is the same thing as this one right here, right? So we get 3 unique products. Wait, let me check the key for this D again for chapter 14. D. Okay, so there's 2 unique products here that they gave us. Let's see what's going on here. Let's see. H plus BR 1 2 3 4 1 2 3 4 1 2 3 4 2 3 4 2 2 that, yep, this, yep. Let's see. HBR. I remember seeing a similar practice problem like this, but the answer was like 3 of these products are. Not sure why there's 2 here. Secondary allylic, allylic, carbocation. Yeah, I think this, I don't know, it should be the other products as well. Like this one should be included, but I'm not sure why they didn't include that here. Your access code. Yeah. If it was thermal, it had been both of the intermediates as well because they're both di-substituted. Yeah. So if this were to be hot conditions, looking for the thermodynamic product or the most stable alkene, both of these alkenes here are di-substituted. So both of these intermediates here would give you the thermodynamic product as well. Right? Yeah. No problem. Okay. Any questions on this problem here? I remember seeing like, I remember there's like 3 products there. I don't know why I'm seeing 2 now, but I remember there's like there were 3 last time I checked this. Let's see, unless they're the same, but I don't think they're the same. Yeah. Okay, let's move on. Any questions on this one? Okay, let's move on. So this one here is going to be another Diels order reaction because we see our diene backbone here and our dienophile backbone here. Let's draw the pocket between the diene and dienophile like that, right? And let's number them 1, 2, 3, 4, 5, 6, right? Where if I draw out the base product, the cyclohexene here, 1, 2, 3, 4, 5, 6, carbon 3 is going to still have that flat methyl group, which is this flat methyl group right here. Now, which one of these groups here on the dienophile is our EWG? What atom holds the EWG? Atom 5 or atom 6 holds the EWG? Right, so atom 6 right here, which is this one, the way I numbered it, is attached to an R group, right? And an R group is going to be considered an EDG, right? By induction. Right, yeah. So any R group like a methyl isopropyl terbutyl is an EDG by induction. if you look at the very first atom here attached to atom 5, that carbonyl carbon is partial positive, making that an EWG, and it can do resonance with a dienophile like that, popping this double bond onto the oxygen. So this is an EWG by induction resonance, right? So this here is our EWG on atom 5. Is this group here on carbon 1 considered an out group or an in group? Out group, right? And we already said earlier that based on the endo rule, they're going to be cis to the EWG. So if I made that a dash group, right, this group on atom 5 would also have to be dash as well. Right, now let's look at the configuration between this R group and this EWG. Are they cis or trans to each other as we see it here? Yeah, so this group here is an out group because if we look at the pocket between the diene and dienophile, the pink dashed lines, this group here is facing outside of the pocket, right? So when we talk about out or in groups, the out or in groups are only going to be on carbons 1 and 4, right? Where the pocket between the diene and dienophile is going to look like that. Any group that is going outside of the pink pocket is considered an out group. Any group that's going inside of the pocket is considered the in group, like that. So that's how you determine what's an out group and what's an in group. And they are only on carbons 1 and 4, right? You cannot say the groups on carbons 2, 3, 5, or 6 are out or in groups. The out or in groups are only on carbons 1 and 4, like that. Right. Okay, so let's look at the configuration between this EWG and this R group. We see that they're cis to each other because they're on the same side of the alkene. So we got to maintain that cis configuration, right? So to make that cis, that has to be dash as well. And then let's connect those together. Boom, boom, boom. I'm going to make this smaller. Boom. Right. And instead of all dashes, this could have been all wedges, giving us a racemic mixture, like that. Okay. Let's see. Let's check the key. Yeah. Any questions on this problem? This one will have 2 products. It's just racemic, right? The 2 products are going to be this and the enantiomer of this. Right, so it's just 2 answers here, 2 products. Right, because let's look at the charges here. On the dienophile, well, this is an intramolecular Diels order reaction. Intramolecular Diels order reaction, right? It's intramolecular because the diene is on the same molecule as the dienophile. The nucleophile is the diene, the electrophile is the dienophile. Since they're on the same molecule and it's attacking itself, it's an intramolecular Diels order reaction, right? So if it's already oriented in this configuration, it's going to react like that, right? We're not going to flip anything because we can't flip that there, right? We can't like flip this structure because it's already given to us intramolecularly. If it was intermolecular, where the diene is separate than the dienophile, then you would look at the charges and see if you could flip them or not. But in the intramolecular Diels order reaction, if it's already given to you like this, where the diene is on the same molecule as the dienophile, you keep it like that. Right. I thought it was a ring closing, so yeah. So this one right here, you could think of it as a ring closing as well, right? Because if we imagine this to be ring closing and we do the conrotatory, this rotatory, you should still get the same answer, right? Because let's say that we did ring closing like this, which means how many pairs of electrons are reacting here? How many degrees of unsaturation are involved in this reaction? 3, right? Which is an odd pair. And I forgot the chart, but an odd pair of electrons or odd degrees of saturation and heat, what does that give you? Con-rotatory or dis-rotatory? Dis-rotatory. Okay. So if it's dis-rotatory, what the what's going on here? Okay. Okay. Let's look at these groups here, right? On carbons 5 and 6. 1, 2, 3, 4, 5, 6. We see that this group here is going up, this group here is going down. They're going away from each other, right? So one's going to go to the left side, my left thumb is going to go to the left side, my right thumb is going to go to the right side. If I rotate my left thumb clockwise, it's going to go up. That means that I'm going to have to rotate my right thumb counterclockwise, opposite direction, right? So that's also going to go up. So we see that they're both cis to each other. So I have to make them both cis to each other like this, right? Now I'm going to try to figure out how we can figure this one out, if it's going to be wedge or dash. Yeah, so in this particular case here, we can't do the thumb rule because there's nothing to compare it to. Like these are two hydrogens, so we can't tell if this is wedge or dash. So don't think of this in terms of electrocyclic ring opening, ring closing. Think of this in terms of an intramolecular Diels-Alder reaction, right? To be able to get all of the correct stereochemistry here. Right. Okay. Yeah. 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 So yeah, don't think of this as ring closing electrocyclic reaction. Think of this as intermolecular Diels-Alder reaction. Okay. So now let's move on to the vocab section. And to save time, I'm just gonna walk through the key and explain each answer, and then let me know what doesn't make sense, and I could explain that concept more because I want to give you guys a practice synthesis problem to try out. So aromatic systems are more or less equally kinetically reactive than a similar conjugated non-aromatic system. So what they're asking for here is that would the intermediate of an aromatic system be more or less stable, right? So let me give you a clear example. If I have a benzene ring here that's aromatic, and then I react it with some kind of electrophile to get this intermediate here, where we broke the aromaticity, versus this conjugated non-aromatic system, like let's say this conjugated diene reacting with some kind of electrophile to form this intermediate. They're asking which one of these intermediates here are going to be, so which one of these intermediates are going to be easier to form? Would it be A or B, right? Would the benzene ring want to break its aromaticity to get A, or would the conjugated diene want to get to this intermediate more likely? Which one is more likely to be formed? Yeah, the conjugated diene is more likely to be formed because this is non-aromatic structure, whereas this benzene is an aromatic structure, right? Where the aromatic structure is more stable than a non-aromatic structure, which is more stable than an anti-aromatic structure. So this aromatic benzene ring here wants to keep its aromaticity. It's less willing to get into this form here. Whereas this conjugated diene here is more willing to get into this form because it was less stable to begin with. Right, so the aromatic system is less kinetically reactive because it doesn't want to get into this intermediate here as much. Can we think of it as like aromatic is just not really reactive compared to alkenes? Yeah, that's actually the best way to think about it, right? Where an aromatic ring is not as reactive as an alkene, and the reason why is because we do not want to break this aromaticity here. That's why aromatic rings are not as reactive as alkenes, because they're super stable, they are aromatic, and we don't want to break that stability. We do not want to break that aromaticity. That's why aromatic rings are less stable than alkenes. So you can think of it like that. That's the best way to think about it. Right. So if they're less reactive, they're gonna be less kinetically reactive. Right. We don't want to form this intermediate as much as this one here. And we already said that this is more stable than this one, so it's more thermodynamically stable, right? Because it's talking about the overall structure. And this is talking about the thermodynamic energy here, right? Where aromatic is more stable than non-aromatic, making it more thermodynamically stable. Okay. Now for part B, right here, they're talking about the Friedel-Crafts reactions limitations, right? Where let's do it like this. Right, let's say this is Friedel-Crafts alkylation, and this is Friedel-Crafts acylation. The limitations for alkylation here is that there's going to be a carbocation rearrangement. That's the biggest one, like a hydride shift, concerted shift, and there's a chance of polysubstitution. Right? In Friedel-Crafts acylation, there's gonna be only one, and that's gonna be the same one as the Friedel-Crafts alkylation reaction, right? And it's that these reactions do not work on deactivated rings. What does it mean for a ring to be deactivated? Right? What group has to be on a ring in order for it to be deactivated? What kind of group deactivates a benzene ring? Right, an EWG, a meta director, such as NO2 or an aldehyde or ketone or any EWG, right? And not all EWGs are meta directors. There's one exception. What EWG do you guys know that is an orthopara director? Halogens, right? Not haloalkanes, halogens, like bromine, chlorine, iodine. Those are deactivators, weak deactivators, but they're orthopara directors, right? Okay. So let me explain to you guys the limitation of Friedel-Crafts alkylation more, because let's say we have this benzene ring right here reacting with this reagent, right? I'm going to show you guys the quick way to predict the product without doing the whole mechanism. In Friedel-Crafts alkylation, always think of a carbocation intermediate, right? Where we see that the leaving group here cannot leave. So to think about this, right? Just this is not the exact mechanism, right? The mechanism is going to be completely different. But to predict the product more quickly, just kick that leaving group out to get this carbocation here. This is not what happens like in the correct mechanism, right? But this will help you get to the correct product. See if that can do a hydride shift, which it can, to form the more stable carbocation intermediate here. Right now, that's the electrophile right there, which is why the benzene ring here is going to attach to that electrophile, right? So that's the answer. It's not going to be this. where some people forget about the carbocation rearrangement and they make this the electrophile, getting that as the answer, right? Where they just put the isopropyl group right there, but it's not that, because that is not doing a rearrangement step. Wait, this is not the correct mechanism. This is just a quick way to predict what the product is. So that was the first thing to look out for, the first limitation, carbocation rearrangement. Now, we added an R group, and then what did we say an R group is? An EDG or an EWG? EDG, right? And is an EDG an activator or a deactivator? Does it make the benzene ring more nucleophilic or less nucleophilic? Activator, right? It's an activator, which means that this benzene ring here can react again with a Friedel-Crafts reagent, right? So it's gonna keep adding on the reagents here. It's gonna keep going on and on and on and on and on, right? Poly substitution, because it's activated. The reason why Friedel-Crafts acylation does not have those two limitations is because, let's say we have this benzene ring here with these Friedel-Crafts acylation reagents here, right? The intermediate is going to be an acylium ion. This could show up on the vocab, like what is the intermediate of Friedel-Crafts acylation, right? What is the electrophile? That is called an acylium ion, right? This acylium ion here, there's no carbocation, therefore there's no carbocation rearrangement. We don't have to worry about that. We don't have to worry about a hydride shift or methyl shift, right? So when we attach the acyl group onto the benzene ring like this, and a tip here to predict the product quickly is look at what the acyl group is and just attach it to the benzene ring, kicking out the chlorine group like that. Another way you can think about it is you're going to substitute the chlorine group with the benzene ring, right? So the acyl group here was attached to a chlorine in the reactant, but now it's attached to the benzene ring there. So those are quick ways to think about the product, to predict the product faster in reactions, to save time on the exam without doing the whole mechanism, right? Now, is this group here an activator or a deactivator? This group that we just added onto the benzene ring. It's an EWG, right? Which is an activator or a deactivator. This EWG here, it's a deactivator, right? So if this benzene ring is deactivated, can we react this again with another Friedel-Crafts reaction? No, we cannot, right? Because we said earlier that Friedel-Crafts reactions do not work on deactivated rings. So it stops here. It only adds once, right? Because when we add it once, we deactivate the ring, so we prevent another Friedel-Crafts reaction from happening, which is why Friedel-Crafts acylation does not have the limitation of polysubstitution. Only Friedel-Crafts alkylation has the problem of polysubstitution and carbocation rearrangement because it has the carbocation intermediate, right? Whereas the Friedel-Crafts acylation has no carbocation intermediate, so no carbocation rearrangement limitation, right? But both of these has the limitation of not working on deactivated rings. Okay, so that's why it's these answers right here: carbocation rearrangement or poly or overalkylation. Reactions are under kinetic control tend to, yeah, I think you guys get this, right? Like kinetics, low heat. And it takes a lot. Wait, what? Kinetic control, low heat and short reaction time, right? It happens the fastest, right? It's the very first thing that gets formed. I think when she made this problem, like there were some request regrades, so she gave her 1 point because the thing was kind of confusing, right? But kinetic products, low energy, less time, low time. The first thing that gets formed. The reaction is controlled by and gives the lowest energy or the more stable. Like another way to say low energy is most stable, lowest energy, most stable, intermediate for kinetic. Right. Let's see. Enthalpy. No, it would be activation energy, right? Because think of it like this. If the kinetic product is the purple thing, it will have lower kinetic energy, but it gives the less stable product, right? Whereas if we look at the red one with more heat, more energy, it has a higher activation energy, but its overall product energy is lower. It's more stable, right? Where this is the graph right here. Reaction coordinate is at the x-axis. Energy is at the y-axis, right? Think of it, the analogy like party before test, and then the test you get a bad score, you're now unstable, unhappy. Whereas in thermodynamic, you spend more time, more energy studying, and then at the end you get a good test score. You're more happy, more stable, right? Where you see here, the activation energy of a kinetic product is lower than the activation energy of the thermodynamic product. You have to put in more energy to become more stable, right? If you put in less energy, you are gonna become less stable. Great. That's an analogy that you can think of. What if it was under thermodynamic control? So if it was under thermodynamic control, it's gonna occur in high and heat, right? Because we need high energy to overcome that big activation energy in order for us to get that more stable product, the thermodynamic product. Right? And it's gonna happen in a long time because it's gonna require time and energy to get to that stable product. So it's gonna happen in a long time. It's also controlled by activation energy because it has to go over that hump from the energy in time. And then the thermodynamic product is going to give us the lowest energy product, aka the most stable product, which is the same thing as the lowest energy product. Right? We see that this is energy, lowest energy products here in thermodynamic. Yeah, long reaction time, lowest energy product requires more heat or energy and time. Okay, next one. Diels order reactions prefer electron-rich dienes and electron-poor dienophiles because in Diels order, the diene is the nucleophile, right? And then to be a strong nucleophile, it has to have a lot of electrons. To be a good electrophile, it has to have less electrons. The diene is always pseudo-cis, aka S-cis, right? So diene always has to be in this S-cis configuration here, not S-trans. Diels order would not work with this S-trans diene, right? The reason why is because the p orbitals will not overlap. The HOMO of the diene, LUMO of the dienophile will not interact. It's too far away. Right? This is too far away. Whereas the S-cis diene is close enough, parallel to the dienophile, so the HOMO of the diene is able to interact with the LUMO of the dienophile. Right. Yeah, no problem. So, and the dienophile will approach the endo orientation in standard conditions. Yes, in room temp, in high temp, high energy, it's gonna reach for the thermodynamic product, right? Which is the exo product. But in standard conditions, like with normal temp and normal everything, well, actually, yeah, you still put heat, but like not extreme heat, not extreme energy and time, right? It's usually gonna go for the endo product, the endo row. So if it said high temperature conditions, then thermo. Yes, if it said extreme high temp conditions, then it would be a thermal product, and you would put exo orientation. You would put exo. Exo if high or extreme temperature, heat, or pressure, extreme conditions. In order to overcome this big activation energy hump to get the thermodynamic product, aka exo product. But in standard conditions, that's why we always draw the endo product for Diels order problems, right? Which is the kinetic product. So in Diels order, in standard conditions, it's always going to give you the endo product. Yeah. Electrocyclic mechanisms will occur in one mechanistic step, like those mechanistic ring around rosy arrows that happen simultaneously. So that's one mechanistic step. And as such, do give predictable stereochemistry with the con rotatory, this rotatory thumb rule, which is how we could predict the stereochemistry of those reactions. Substituents para to an electrophile, added electrophile, will have direct interaction with the intermediate cation in the electrophilic amount substitution. Right, so what that's saying is that if we have a benzene ring here with an electrophile and some kind of group para to it, if we try to put another electrophile in, would that be affected? Like, would the benzene be directing the group somewhere? And it will, because if we have an EDG, it will direct the group orthopara. If we have an EWG, it would direct the group meta, unless it's a halogen, right? Where in EAS reactions, benzenes are going to be nucleophiles. So to make the EAS reaction faster, how can we make the benzene ring a better nucleophile? What kind of group do we want to add onto the benzene ring to make it a better nucleophile? EDG or EWG? EDG, yes. And then to make it a weaker nucleophile, then we added EWG to deactivate it. Yeah, that's right. Okay. So let's see. Yeah, this will slow down the reaction if the substitute is NO2, because NO2 here is an EWG. That's different than NH2. If it were to be NH2, then that is an EDG, which would speed up the reaction. So make sure to keep those differences in mind. NO2 versus NH2. NO2 right here is an EWG, and H2 is an EDG. The electrophile here does not matter. The electrophile does not affect the reaction rate at all, right? So the electrophile here is coming from a nitration reaction, right? That's nitration. It could also be like an electrophile from halogenation, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. Any electrophile does not affect the reaction rate at all. The nucleophile of the benzene affects the reaction rate, right? And that depends on the EDG or EWG. Okay, let me show you the thumb rule table really quick. Right here. Should copy this. Paste. There you go. Yeah. I would include this table and this table on your note card if you have trouble figuring out where to start and end your thumbs. Yeah. Yeah. Uh-huh. Another table that I would add is this right here. No. The aromatic, anti-aromatic versus non-aromatic thing. This one. Yeah, that's another table I would add in the note card to determine or identify if a molecule is aromatic, anti-aromatic, or non-aromatic. There's 3 weird scenarios for this, right? Especially the non-planar ones. And I think for lecture, Levens gave a list of non-planar molecules, which are automatically non-aromatic, right? So just put all those lists of non-planar molecules down in the card as well, so you don't get tripped up on that, right? Like the cyclooctatetraene and this weird structure here, that's also non-planar. Put all the non-planar structures down, so you will automatically say that those structures are non-aromatic because they do not fulfill this condition here. Yeah. Yeah. Uh-huh. So it wouldn't change if the electrophile is different because the substituent will slow down the reaction regardless. So the substituent will slow down the reaction if the substituent is an EWG, a deactivator. That's when it will slow down the reaction. if the substituent was an EDG, an activator, the reaction rate will increase, right? The electrophile is not touching the reaction rate at all, because in EAS reactions, the benzene here is the nucleophile that is attacking the electrophile, making this intermediate here, where we break the aromaticity. And then some kind of base will restore that aromaticity, depending on what the reagents are in the solution. Make sure to know all the EAS mechanisms: halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts isolation, because I think that one of those will be tested on tomorrow's midterm, right? One of those EAS mechanisms will be tested. Make sure to know all those mechanisms. Write that down on your note card, right? Halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts isolation, right? Where the benzene here is the nucleophile, where if there's an EDG on the benzene ring, that increases the reaction rate, right? So let's say I put R, oh shit, this is right here. R, well, this is kind of misleading because, okay, let me just say R. If it's an EDG, it's gonna increase the reaction rate because it's an activator. If it's an EWG, it's gonna decrease the reaction rate because it deactivates the ring. Right, the electrophile here does not affect the reaction rate at all. This electrophile could be anything, right, depending on what the reaction is. Yeah. Electrophile does not affect EAS reaction rate. Okay. So the electrophile doesn't impact the reaction rate. Yes. Electrophile does not impact or affect the reaction rate. The R group on the benzene does affect the reaction rate because it activates or deactivates the ring, making it faster or slower. Right? The electrophile is not part of the benzene ring. The electrophile is being attacked by the benzene ring in the mechanism. Hopefully that makes sense. Okay. Yeah, because this electrophile here is the one being attacked by this benzene ring. And what affects this benzene ring is what type of group is attached to it: an activator, an EDG, or a deactivator, an EWG. Right? Yeah. Okay. That's good. Yeah. So that's that part of the vocab section. Let's see. Okay. Allylic systems stabilize all of these because allylic systems can do resonance with anions, like this, radicals like this, and cations like that, and even double bonds like that. So negative charge anions, positive charge cations, radicals, and even double bonds can do resonance during reactions and increase reaction rates. Right, so this is talking about nucleophilic SN1 reaction, right? Where if you try to do an SN1 reaction with this primary halocane with water, no reaction. But if your primary halocane is allylic and you react it with water, you're gonna get these two products. Right, because this carbocation is not stable when the leaving group leaves, forming this carbocation, which is able to do resonance to get the other resonance structure here, right? And this resonance structure would lead us to this product. This resonance structure would lead us to that product there, right? Where the water would attack those carbocations, giving us our two different products, right? So that's why it increases the reaction rate if the substrate or electrophile is allylic. That's the most important concept there. The allylic position, right? Increases reaction rate, right? Both SN1 and SN2. Okay. What's going on here? Increase a secondary allylic cation is approximately equivalent to the internal energy of a tertiary alkyl cation. Okay. So what she's saying here is that this secondary allylic carbocation is approximately equal in stability with that tertiary carbocation that is not allylic, right? And the reason why is because this secondary allylic position can do resonance, and resonance increases the stability, right? So here's a chart that might help you guys out. Let's say you have a methyl carbocation, primary carbocation, secondary carbocation, tertiary carbocation, and I would say a secondary allylic carbocation is a little bit more stable, and then the most stable one, tertiary carbocation, tertiary allylic carbocation, there, right? Unsub, mono, di, tri, secondary allylic, tertiary allylic, right? Where we see the allylic carbocations are the most stable because they can do resonance, right? Okay. Tertiary carbocation. It's not primary or secondary because a secondary allylic carbocation is way more stable than a primary and secondary carbocation that cannot do resonance, right? So it's on par or even better than a tertiary alkyl cation that cannot do resonance. Aromatic substances involve cyclic, 4n+2, always planar. So this is talking about the chart that I just showed you guys here with the 4n+2, cyclic, always planar, always fully conjugated conditions to be considered aromatic. Conjugated dienes freely rotate around the central bonds similarly to sigma bonds. So this is false because when we look at this conjugated system here, we see that it could do resonance like this, giving us this resonance structure, right? Where we see this highlighted portion here has a bond order of 1.5, right? So it's a mix between a single bond and a double bond, right? So it can't freely rotate as much as a single bond like this because it's purely a single bond, which has all free rotation. This is not purely a single bond because when we draw its resonance structure, we see a double bond character right there, which restricts the rotation a little bit. So it's less freely rotatable, less freely rotatable. Aromatics are never rotatable, right? Because aromatics are all cyclic and we cannot rotate rings. We can never rotate rings. Aromatics are always cyclic, so we can never rotate that ring, right? But conjugated systems like this that are not cyclic, they can rotate a little bit, requiring enough energy, but not as much as a pure single bond like that, right? Because when we draw its resonance structure, we see that that has double bond character, restricting the rotation of it. Okay. Delocalization uses at least 3 parallel adjacent p orbitals, right? Because delocalization is going to be a network of at least 3 parallel p orbitals. 1, 2, 3. Yeah. Any questions on that? I think we went over that a lot in the last videos or office hours. Right. Okay. Are you guys familiar with the synthesis problem here on the practice exam? Like how we approach these this practice problem here? No, not mechanism. Synthesis? No. Okay. So let's go over this right here. We see that the similarities between this product and this reactant and this product is that chain right there, right? So now let's look at the differences. We see that we added new R groups and chlorine. What reaction do you guys think of? Oh, J of the vocab section or J of which part? Oh, J, this one. Yeah. So J right here, delocalization is going to be using at least 3 parallel adjacent p orbitals. One of my videos on YouTube explained this more in detail, but what this is basically saying is that this conjugated system here has a network of p orbitals, at least 3, that are able to do resonance with each other, right? And it has to be at least 3 adjacent p orbitals, right? 5. the pi electrons. Oh, yeah. So let's see. Okay, yeah, I think we can do this quickly. Let's draw out all the p orbitals like this: p orbital, 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 p, p orbital, 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 p orbital. Right. So I'm gonna highlight the ones that have a network of at least 3 parallel adjacent p orbitals. Right. That's one. This is another one. This is another one. This is another one. This is another one. That's another one. Right. This oh, sp3 roadblock. Right. sp3 roadblock blocking resonance is gonna be the axis. Right. There's only 2 here. That's not 3. So that's not delocalized. sp3 roadblock, sp3 roadblock. There's 3 p orbitals, but they're not adjacent to each other. There's sp3 roadblocks blocking them. There's 4 p orbitals here, but there's no adjacent 3 p orbitals, right? The most adjacent thing we have is 2 p orbitals. That sp3 is blocking them from being conjugated or delocalized, right? Okay. Yeah, so I don't think I have more time to go over the other problems of this practice exam, but I will go over the synthesis problem really quick, and then I'll give you guys a similar synthesis problem. It's a little bit longer than this one, but I'll walk you guys through that as well, and then we'll call it office hours, right? So what reaction do you guys think we used to put 2 halogens on this system right here? Right? Like what reactant came from this portion here? When you see 2 halogens like this, think of like 1,4 addition, 1,2 addition. Yep, it's gonna be HBr excess or Br2, but in this case, it's gonna be Cl2, Cl2. So we used a Cl2 here because we added 2 chlorines, right? So it's gonna be either in hot or cold conditions, right? Yes, it's gonna be cold, and then to figure out what it is, let's highlight that portion right there. Let's say that we made a conjugated system extending this chain out like this. What reaction do you guys know that can make a conjugated system? This is the end of chapter 13, segueing into chapter 14, the Heck reaction. Yes. Which means that we're going to use the Heck reaction reagents, 1% palladium, OAC2, PR3, heat, and then I'm going to make that this connection right there, where this whole portion here is going to be this alkene right there, right? Where this star nucleophile is that star nucleophile, this dot electrophile is that dot electrophile, and that's the new bond that gets formed between them, right? Combining the star and dot carbons together to make that conjugated diene. Okay, and then if we want the Cl to be on these positions here, try out the mechanism, both kinetic and thermodynamic products. You're gonna see that we want the kinetic product, right? But try that for practice. Try drawing out the whole mechanism, right? In hot and cold conditions. If we want this one right here, we're gonna use Cl2 1 equivalents in cold conditions, right? Now, what is one reaction you guys know that adds a nitrogen to the benzene ring? What EAS reaction adds a nitrogen to the benzene ring? Nitration, right? So that's going to be HNO3, H2SO4, where now the reason why we're going to add it para to this group here is because think of this group as an R group, right? The very first atom attached to the system is an R group that's not a carbonyl, which is an EDG, an ortho paraductor. We're going to direct the electrophile to the para position because it's the least sterically hindered side, the most major side, right? So that EDG right there is going to direct the NO2 to the para position, the less sterically hindered side. Okay, now what can we do to convert this NO2 to NH2 and get rid of this alkene to the alkane right there? Right. H2 and with what? Like we can't just put H2 because H2 is a gas that will not do anything. H2PD, right? Metal catalyst. This PD here is important. That metal catalyst will allow the reaction to occur. Right. Now, I made a similar synthesis problem for you guys to try. That's very close to this, but it's going to be a little bit more involved, right? It's going to require more reactions. So let me give that to you guys here. Okay, and let me give you guys the arrows and boxes too. It's going to be 7 intermediates. Eight steps, 1, 2, 3, 4, 5, 6, 7, 8. Okay, does H2PD also change NH2 to NO2? Or so H2PD or FeHCl would convert the NO2 to NH2. If you want to convert the NH2 back to NO2, then you gotta use CF3CO3H or MCPBA, right? And then that's gonna talk all about these helper reactions here. Right here, right? Where if you wanted to convert NH2 to NO2, you use CF3CO3H or MCPBA. And then if you wanted to convert an alkyl group back to a carbonyl, you gotta use Jones, right? But FeHCl, H2PD, or zinc mercury HCl would reduce NO2 to NH2 and the carbonyl down to alkyl group like that, right? Okay. So now let's try this big synthesis problem, the boss battle. So what can we do to get this big alkyl group here, where we see two chlorines 1, 4 to each other, 1, 2, 3, 4. What reaction do you think happened in the first step that made this extended R chain with two halogens attached to it? It's very similar to the very first synthesis we did, Heck reaction, right? Where we're gonna use 1% PD OAC to PR3 heat. And the alkene we use, like let's say this is the star carbon, this is the dot carbon. The dot carbon is the alkene there, right? Because that's the new one that gets formed, going backwards or forwards a little bit, right? That's gonna give us this conjugated diene here. So star, new bond, dot, like that. And we have to maintain that trans alkene. We have to make it trans alkene. Now, what reagents do you think we could do to add the chlorines on these positions here? And in what conditions? Hot or cold conditions? CO2, yep, it would be CO2, 1 equivalent. It has to be 1 equivalent because we're only adding CO2 once. So it has to be 1 equivalent. In hot or cold temperature? This is the most challenging part here, determining what kind of conditions we want. Yeah, so if we did this in cold temperature, let me actually do this out in both cold and hot temperature. Right, this is an asymmetrical diene here, and I'm gonna tell you guys that this is the best resonance set here. Right, this alkene here is gonna give us our best resonance set, so I'm not gonna do the other alkene. Right, and then we're gonna make this carbocation over here, which is a tertiary allylic carbocation. Oh wait, no, there's no CO there. Positive charge that can do resonance like this, giving us this best resonance set here. Carbocation there, right? Where this carbocation is tertiary allylic, this is secondary allylic. If you reacted with this double bond, you would have gotten a secondary allylic carbocation and a secondary allylic carbocation, right? You would have had this carbocation and this carbocation here, and they're both secondary allylic. That's a worse resonance set than this one here, because this resonance set has a tertiary allylic carbocation and a secondary allylic carbocation, right? Where we see that we want this intermediate here, right? Because we want the Cl minus to attack this position right here. Where would this intermediate be the kinetic intermediate or the thermodynamic intermediate? Right, let's also label the alkene. This is a di sub alkene. This is a tri sub alkene. Thermo, right? Because we want the more stable alkene right here. So we're gonna react this in hot conditions, right? Which is gonna give us this product. Okay. So now, what can we do to, let's say, get rid of this double bond here? What reaction can we do to get rid of that double bond? Think back to the midterm 1 material. Yeah, so it's hot because we want the thermodynamic product. Since the thermodynamic product would give us the chlorines on the correct position we want on the products, right? Since the product had the chlorines on these positions, we want the chlorines there. And to put the chlorines here with CO2, we want the thermodynamic product, which gives the CO2 CLs on both of those carbons, which is the thermodynamic product, right? The more stable alkene right there. If we did cold, right, the cold conditions would give us this product here, which will put the chlorines on the wrong position, right? We don't want the chlorines here. That's the wrong position. They're too close to each other, right? So you gotta look at where your chlorines are in the product. Yep, H2PD, H2PD, right? But H2PD would not only reduce the alkene down, it would also reduce the carbonyl down. So you're gonna completely get rid of that carbonyl. Right, so now we do have our chlorines on the right positions. How can we add a nitro group onto the benzene ring, right? So that's gonna be nitration. But what's the problem here? If I did nitration, it's gonna add either to the ortho or para position, because what is this group here? is this? Yeah, it's an R group, which is the EDG. And then to block this para position right here, like someone said, we're gonna have to block that para position by using sulfonation, right? So we don't want any group at the para position because there's no group at the para position here. We gotta block that. We gotta protect that position. To protect that position, we use sulfonation. SO3, H2, SO4. Right, which we put SO3 at the para position here. And now we could do nitration to add the nitro group to the ortho position. Right, without worrying about adding something to the para position because it's already blocked off by the para position in O2. Okay. Now, once we have this group, what can we do to get rid of this sulfonate group? How can we deprotect the para position? Because we don't want anything in the para position at the end. Yes, desulfonation or hydrolysis using reagents H2SO4, water, and heat. And that's going to completely deprotect the para position, get rid of the sulfonate group. Right, because it's already served its purpose by protecting that para position, preventing the NO2 to go to that position. Okay, NO2. Now, how can we convert this NO2 to NH2? Yeah, the H2PD got rid of the carbonyl. H2PD would get rid of the carbonyl, and H2PD would reduce an NO2 to NH2, and H2PD would get rid of an alkene overall. Yeah, yeah. FeHCl would be one reagent you could use. Another reagent you could use is zinc, mercury, HCl, or you could also use H2PD, one of the reducing agents here, H2PD, which would convert the NO2 into NH2. Right? Okay, now final step here. How can we get our carbonyl back? How can we summon our carbonyl back? Jones, yeah. CrO3, H2SO4, water. So that was the 8-step synthesis right there. Right. Yeah. This H2PD here, it did two things. It got rid of the alkene and it got rid of the carbonyl. And in this specific case right here, we had to use H2PD, right, to get rid of the alkene and the carbonyl. We can't use FeHCl or zinc mercury HCl because those two reagents here would not get rid of the alkene. We had to specifically use H2PD to get rid of both the carbonyl and the alkene in this case, in this reaction. Okay. Good luck with the final tomorrow morning. What are you guys planning to do now? Like study more, or what time are you guys planning to sleep? No sleep? Oh shoot. Yeah, I think I'm gonna stay up really late too because I'm not ready for my test tomorrow. So I'm gonna stay up pretty late tonight too. Make the note card, study more, practice nomenclature NMR, index. Oh yeah, study more. Let's see. Okay. Shoot. I'll post the video and notes to this under the Discord once it's up. But yeah, I hope the exam goes well for you guys tomorrow, and good luck. For synthesis practice, let's see, Leibniz synthesis practice are cumulative, so that's not really good for the midterm 2 material because like there's some reactions you haven't learned yet. Let's see. Maria Jones worksheets are good as well. I think Maria Jones worksheets are good for synthesis, the AECC Maria Jones ones. Yeah. No problem. Yeah. Yep. Good luck, everyone. See ya. Thank you. So I'm gonna go end off a little bit early because I need to study for my exam. But tomorrow, I think there's gonna be like less people showing up, so we could talk and study more tomorrow, Ryan. But how's your day today, Ryan? Okay, yeah. Well, I will see you tomorrow. I'm gonna study for my exam now. And yeah. Good night. Good night. Good night.